The key words or important key statements. 1. Frame of reference. Frame of reference is the coordinate that describe the position of an object. Sets of coordinates. Space and time coordinates. X, Y, Z are the space coordinate and T for time. Number 2. The initial frame of reference. It obeys Newton's first law. Objects won't accelerate unless they are acted on by external force. Stationary and constant velocity or constant motion. That means no acceleration. 3. Inertia is a property of matter by which it remains at rest or at uniform motion in a straight line unless acted upon by an external force. 4. Einstein's theory of special relativity only works in inertial frames and is based on two postulates, assumptions. A. The laws of physics is the same in all inertial frames. B. Speed of light in free space, that is vacuum, is invariant. Invariant means same or constant for all inertial observers or sources. The Lorentz transformation, which is compatible with special relativity theory, was invented by Voigt in 1887 and adopted by Lorentz in 1904 and applied by Poincare in 1906. Einstein probably picked it up from Voigt directly. If you have two inertial frame of reference, S will be stationary, S prime will travel off with a velocity v, both starting from the same inertial frame of reference point, 0 and 0 prime. We have observer A in S frame of reference, observer B in S prime frame of reference. The X is parallel to X prime and Y is parallel to Y prime and Z is parallel to Z prime. So the two events start from the same frame of reference, X, Y, Z, and T, and then the S prime moved with a velocity v. If an event happens in S prime frame of reference, then the observer A from S frame of reference will also see the different event in a different manner. So we're going to calculate, or we're going to derive the transformation of what observer A will see when events take place in S prime. Requirement. Consider the Galilean transformation where x prime is equal to x minus vt. The function of x prime is dependent on x and t. The function of x prime must be linear and one-to-one relationship. Therefore, no acceleration from first postulate. So the assumption is to start x prime with a function ax plus bt, and that will be the first equation, where we need to find a and b which are constant. So we can start with x equals vt for observer A when s prime moves off with a velocity v. And because we're looking at events taking place in s prime, then x prime will be equal to 0. Using the equation 1, which we know to be x prime equals ax plus bt, because we know x prime is a function of x and t, we can then substitute the x equals vt and x prime equal to 0 into equation 1. Therefore, x prime is 0 equals to a vt. Vt is x plus bt. So the common factor here is t. And then, so if we take bt to the other side, or leave bt there and take minus a vt to the other side, bt equals minus a vt. Since t is common in both sides, we can cancel t out. B equals minus AV. If we substitute equation 2 back into equation 1, x prime equals to AX plus minus AV times t. And if we expand that, the x prime equals AX minus AVT. A is a common factor here. Therefore, x prime equals A open bracket x minus VT close bracket, and that will be equation 3 to find A, because we don't know what A is. That represents the Galilean equation for x prime, which is x minus vt, but this time it's multiplied by a factor, and this A will be a Lorentz factor. That's what we need to find. So the reverse transformation will be exactly the same, but we have to make x rather than x prime. So the v prime is minus v because it's going in the opposite direction of v, going back from here to s. So we're going from s prime to s. So we would write the x, which is, instead of writing x prime, we write x equals to a open bracket x prime minus v prime t prime. But v prime is minus v, so we write x equals to a x prime minus v prime, but because v prime is minus v, it will become plus v t prime. Let that be equation 4. Now applying second postulate, which says the speed of light is constant. When an event happens here or there, they will see the speed of light the same. Therefore, we can say for the s, which is at rest, the x is going to be ct, and for s prime, which is with a velocity, for s prime, x prime is equal to ct prime. This is equation 5 and 6. Now we can substitute 5 and 6 into equation 3. Here we will get ct prime equals to a open bracket ct minus vt. As you can see, this is equation 3 here. X is ct and x prime is ct prime, since we're applying the second postulate, which is referring to speed of light, which is constant for all inertial observer. So when we substitute equation 5 and 6 into equation 3, this is what we got. Now what we need to do is find the ratio of t over t prime, and to find the ratio of t over t prime, we need to divide both sides by t prime and divide both sides by a open bracket c minus v close bracket. So that's what we get from there. So that's the ratio of t over t prime. At the same time, we now need to substitute equation 5 and 6 into equation 4. This is equation 4. We know x is ct, where c is the speed of light, open bracket c times t prime plus v. Now t prime is a common factor, and now we want the ratio of t over t prime, just like we did here. And t over t prime is equal to a open bracket c plus v close bracket over c. We're going to equate these two equations together since these ratios are the same, so that will be equal to that. Now we multiply both sides by c to get rid of that denominator, and multiply both sides by a open bracket c minus v to get rid of that denominator, and that's what we get. But we do remember that dots, which means difference of two squares, is if you have m plus m open bracket close bracket times m minus n open bracket close bracket, that will be equal to n squared minus m squared. We have the same here, so that will be equal to c squared plus a squared open bracket c squared minus v squared close bracket. And therefore we're making a squared the subject, which means dividing both sides by c squared minus v squared. And we need to take c squared out as a common factor. This is what we get, because if I divide that by c squared, I get 1. If I divide that by c squared, I get 1. If I divide that by c squared, I get v squared over c squared. So basically, I'm dividing both sides here, the denominator by c squared. And that's why I get this 1 minus v squared over c squared. C squared cancel out, so we get a squared equals to 1 over 1 minus v squared over c squared. And we find a to be 1 over root 1 minus v squared over c squared. Remember, c squared, c is the speed of light, v is the velocity of s prime frame of reference. A is what we called the gamma. So a is now gamma, what we called Lorentz factor. Take equation 3 and 4, which are, as equation 3, x prime equals a open bracket x minus vt close bracket. And equation 3 now, we replace that a with gamma. Now if we look at equation 4, which is x equals gamma open bracket x prime plus v t prime close bracket. Now we can find t prime and t. This is Lorentz transformation, the x prime, and this is the reverse Lorentz transformation. Now we're going to find the time prime, the Lorentz transformation, and t will be the reverse Lorentz transformation for time. We know x prime equals to x minus vt over root 1 minus v squared over c squared, because we're multiplying it by gamma, and gamma is 1 over root 1 minus v squared over c squared. We find the reverse transformation. Again, you multiply by gamma, which is that one, and if we substitute equation 7 into equation 8. This is equation 7, and we're going to substitute that into equation 8. This is equation 8, and so that will be replaced by this bit here. So first thing is to multiply both sides by root 1 minus v squared over c squared. So multiply that by that, and I get this. And now I'm going to substitute that. I'm going to substitute that into here, which I get that. Now I need to multiply both sides by, again, root 1 minus v squared over c squared. So that times that. The root will go, and that times that. So I get that and that. I need to expand this bit here. So that expanded, and we still get that here. Now I need to bring this over here and that over there. So x minus x plus vt minus xv squared over c squared equals that. Now that will cancel each other. V is a common factor here. Therefore t, because v is gone there, v is gone there. So that's gone. So t equals x v over c squared equals to t prime root 1 minus v squared over c squared. So now I'm going to divide both sides by root 1 minus v squared over c squared to get t prime, and therefore that's the equation. Now t prime is equal to t minus xv over c squared, they're all divided by root 1 minus v squared over c squared, but 1 over root 1 minus v squared over c squared is gamma. Therefore we can say t prime equals gamma times open bracket t minus x v over c squared close bracket. We can now do the reverse transformation for time, which is gamma open bracket t prime minus x prime v prime, but v prime is minus v, so that becomes plus v over c squared. Lorentz transformation from s to s prime, if we start with knowing that gamma, because we found gamma, and we can then transform the x to x prime by using x equals y open bracket x prime plus v t prime close bracket, where y is y prime and z is z prime because there's no translation in both y and z, and t open bracket t prime plus x prime v over c squared. This is reverse transformation for time. This is reverse Lorentz transformation, and that's reverse Lorentz transformation. So we're transforming that into Lorentz transformation, and then we get the x prime, which is gamma open bracket x minus vt close bracket, y prime equals y, z prime equals z, t prime open bracket t minus x v over c squared close bracket. So this is Lorentz transformation. It is this transformation we're going to use in length contraction, time dilation, and this transformation is compatible with special relativity theory.